Um, we're nearing the end of Engineering Math A, and the last module in Math A is integral vector, vector calculus. And the last part of that is integral vector calculus. And the way I taught it, we really only covered two big things in integral vector calculus, the work integral and the flux integral. And we talked about various methods of doing the work integral, and we had various formulas for doing the flux integral. There's two big things left to cover. One is Stokes theorem, and the other is the divergence theorem. Well, let me cover Stokes theorem in this video. If you recall Green's theorem for doing a work integral, we converted a work integral to a double integral. Here was the formula for it, Green's theorem. And it said if you have a closed curve, this only worked when you have a closed curve in two dimensions, the Green's theorem. And it says that work integral around this path, or curve C, is the double integral over this region R. This R is that region enclosed by the curve. Stokes' theorem generalizes that to a three-dimensional vector field. Here's the work integral, and here's what it is as a surface integral. Again, it only works if you have a closed path, and you can use any surface that has that edge, that closed curve, as an edge. And the region, well, when you use the PQR method, the region of integration will be the shadow of that surface onto the XY plane. But here's the basics of the Stokes theorem. You can convert a work integral to a flux integral. Where instead of where we would normally have F here for the flux integral, it's now the curl of this F. And by the way, this surface, I already mentioned it, it can be any surface that has that closed curve as its edge. We're only going to use PQR method when we compute this, either that or the direct method. Curl F out of N is a constant, and you know the area of the surface, we can use the direct method. Otherwise, I only use it when Z is a function of X and Y, when the surface can be expressed. So yeah, when I did Stokes problems in my class, they either broke down when you did the flux part of the problem, you'd either use the PQR method or the direct method, not use the general method in my class. I guess you could if you wanted to. Here's all it means. If you can do this, which is a flux integral, any way you want, you can still do it. So let's do an example. Here's the vector field, and the curve is this wire frame here. Now we're given the curve with the arrows on it, which is the edge of this thing. The surface we'll pick is just this flat piece of a plane. We could have picked some other weird surface for some reason, but the easy thing to do is this flat plane. So when we use the PQR method, what is going to be our region of integration? Remember, we integrate, when we use PQR, the region of integration is in the XY plane somewhere. It's going to be this rectangle down in the XY plane. Projection of this surface up here down onto the XY plane, like a shadow. Well, let's see. Our P is XY, our Q is YZ, our R is XZ, And surface is z equals 1 minus y. Every place there's a z in here, we have to replace it with 1 minus y. Where's our, well, before we do that, let's find the curl. That's what really goes into the formula. Heck, did I do that? Yeah, what I do is I put hats on the F. This is really the curl of F. So we're still using the PQR formula, but the PQ and R come from the curl of F, not F. First, we have to find the curl of F. Here's the formula for finding a curl. Remember, take that determinant, yada, yada, yada. Here's what you get. P is minus 2y, Q is minus z, R is minus x. And wherever there's a z, we have to replace it with z is, 1 minus y. Here is going to be our curl of F, P hat, Q hat, R hat. And what's the partial of z with respect to x? 0. With respect to y, it's just minus 1. So here we have all the pieces, the partials, the P, Q, and R hats. Put them into our formula, PQR formula. There it is. There's the integrand, and R is just, I said, this rectangle down in the XY plane. X will go from 0 to 2, and Y will go at 1. Y goes from 0 to 1. Y, for some reason, integrated over Y first. Y goes from 0 to 1, X goes from 0 to 2. There's our setup. That's the important part to get to. After right here, it's just a normal double integral. I won't go through that. The answer is minus 3, negative 3. One more example of Stokes. Here's our F, our vector field, and C is a counterclockwise trace of the cylinder squared plus y squared equals 1 in the plane x plus y plus z equals 1. This one's kind of certainly hard to draw in 3 dimensions. It's a little bit hard to imagine. So first, let's see, we've got a cylinder of radius 1. So you at least imagine the cylinder, right? It goes along the z-axis, radius of 1. But then we're going to slice through that with this plane. So, and then wherever those two guys intersect, that's our curve. You don't have to draw it exactly, because what's important is the region of integration, which is in the xy plane. That's going to be just a circle of radius 1. We'll use this for the formula for the surface. We'll have z equals 1 minus x minus y. So here's our surface. Partials are easy enough, minus 1 and minus 1. There's our partials. Here's the F, y cubed minus x cubed plus z cubed. Find its curl. And it's all in k direction. I guess the x's and y's are zeros. So there it is in terms of x and y. Here's our curl. So P is 0, Q is 0, and we've got an R. Plug them in. So here's our P hat, our Q hat, and our R hat. That's what we plug into the PQR formula. And the P and Q parts go away because they're zeros, so we're only left with the R part, and it is this. And R is the unit circle, so we'll use polar coordinates. X squared plus y squared is r squared. dA is the extra r dr d theta. So this is, there it is, easy enough. That double integral breaks up into a product. We're done. That's how it works. And that's Stokes theorem as deeply as I covered it. So we're only left with the divergence theorem, and that will pretty much end engineering math A.